Okay, so let us start today's session. In the last session, okay, we have seen this schematic diagram as well as TS diagram for a bootstrap air cooling system. Okay, so when you compare this bootstrap air cooling system, okay, with simple air cooling system, what additional thing which you have, okay, is nothing but this compressor, okay, and this additional heat exchanger. Okay, so due to this addition of secondary compressor and secondary heat exchanger, okay, this system is known as bootstrap air cooling system. Okay, so based on these changes, obviously our TS diagram is going to change. So all this we have seen in the last session. Okay, now for this session, what we'll do is we will see a problem based on bootstrap air cooling system. Okay, so as you can see on the screen, okay, you can just start reading the problem. Okay, so let us see the problem. Okay, what is the problem is a bootstrap cooling system of 10 TR capacity is used in aeroplane. Okay, so at the starting only they have mentioned that it's a bootstrap cooling system. Okay, so see, just starting word, it's a bootstrap cooling system. Okay, so when they mention that it's a bootstrap cooling system, obviously you should be able to draw this schematic diagram. Okay, so once you are able to draw this schematic diagram, okay, the TS diagrams becomes very easy to draw. Okay, so draw the schematic diagram. Okay, so if you are able to draw the schematic diagram, okay, you will be able to correctly plot the points on the TS diagram. Okay, so both are essential, okay, so as to solve the problem. Okay, so bootstrap air cooling system. Okay, so this is a bootstrap air cooling system. You can see the schematic diagram. Okay, the ambient air will come at point number 1. As you can see, the ambient air will come at point number 1. Okay, then it will be get rammed. Okay, so once it is getting rammed, I will show it by point number 2. So after ramming, it will comes at point number 2. Okay, then it will get compressed in a compressor, so it will comes out at point number 3. Okay, basic point you should be able to locate. Basic points you should be able to locate. Now once it is getting out of the compressor, okay, it will goes to where? It will goes to heat exchanger, and it will comes out at point number 4 from the heat exchanger. Okay, it will comes out from the point number 4 from the heat exchanger. Okay, now once it is coming out of the heat exchanger, it is supplied to the secondary compressor. In compressor, it will be get compressed, and it will comes out at point number 5. Okay, now from the secondary compressor, it is supplied to secondary heat exchanger, where again it's get cooled. Okay, so it will be come out at point number 6. Okay, now once it is getting out of the point number 6, it is further supplied to the cooling turbine, where it is get cooled. Okay, so the point number 7, I will call this as an exit to the turbine. Okay, point number 7 is the exit to the turbine, and from the point number 7, okay, it is supplied to the cabin. Okay, so where the air goes to the cabin. So here somewhere, okay, I will mark the diagram for the cabin. This is your cabin, right? So from the cabin, okay, the air comes out at point number 8. Okay, so this is a schematic diagram what we have plotted. Same you can see on the TS diagram. See, 1 to 2 it's a ramming, 1 to 2 it's a ramming. Okay, 1 to 2 it's a ideal ramming, 1 to 2 dash is the actual ramming. Okay, so this point 2 can be also 2 dash, this point 2 also can be 2 dash, right? 2 stands for ideal, 2 dash stands for actual. Similarly, okay, we can have the compression from 2 dash to 3. 2 dash to 3 is the ideal. Okay, so 2 dash to 3 is the ideal, and 2 dash to 3 dash is the actual. Okay, see, 2 dash to 3 it's ideal, 2 dash to 3 dash it's the actual compression. Okay, next, okay, from 3 or 3 dash we will go to point number 4. Okay, that is a cooling in a heat exchanger. From point number 4, as you can see, okay, from point number 4 we will compress it in a compressor. Okay, so again that compression, that is from 4 to 5, it can be ideal or it can be actual. Okay, so 4 to 5 it's the ideal compression, 4 to 5 dash is the actual compression. Okay, so this point you can mark this as 5 or 5 dash, right? This point can be 5 or this also can be 5 dash. 5 stands for ideal, 5 dash stands for actual. Okay, Now, once it is getting out of the compressor, we will supply it to the heat exchanger. Okay, so it will comes out at point number 6. So you can see the point number 6. Now from point number 6, we will supply it to the turbine. So it will get cooled. Okay, so from 6 to 7, what happens? It gets cooled. So 6 to 7, as you can see, 6 to 7, it's the ideal cooling. Okay, and 6 to 7 dash, it's the actual cooling, right? And similarly, once it is getting out of the turbine, as you can see, it is supplied to the cabin. Okay, and in cabin, what happens? Okay, the cabin gets cooled, but air gets heated. Okay, air gets heated. So you will get a temperature at point number 8, which is greater than temperature at point number 7. Okay, so when temperature of the air increases, what happens? The cabin gets cooled. Okay, so is that okay with this diagram? Yes, I just revised it. Yeah, is that okay? Yes, let me know. Is that okay with the diagram? All of you? Okay. So now let us start with the problem. Okay, a bootstrap cooling system of 10 TR. Okay, so 10 TR, it is nothing but a refrigeration effect. Okay, 10 TR is what? We want a refrigerating capacity of 10 ton. Okay, so that is nothing but Q. Okay, so Q, I will mention it as 10 TR. Q is 10 TR. So QR is nothing but what? Okay, Q is a refrigerating effect. So we want a refrigerating effect of 10 ton. Obviously, this is 10 ton. Okay, we need to convert that into kilojoule per minute. Okay, so we will multiply it by 210. So it will be in kilojoule per minute. So that thing we will do it later on. Okay, let us go to the next point. The ambient air temperature and pressure are 20 degrees Celsius and 0.8 bar. Okay, so what temperature you have? I'll just mention here. Temperature T1 is given by 20 degrees Celsius. Okay, ambient, you can see the ambient air temperature and pressure. So ambient is what? It is a condition 1, where we have temperature 20 degrees Celsius. So that is nothing but, okay, 20 plus 273, that is 293 Kelvin. I'll just write down directly. Okay, and pressure is 0.85 bar. Okay, so pressure P1 I'll just write down as 0.85 bar, and 0.85 bar, it is nothing but, okay, 85 kilopascal. Okay, just multiplied by 100, so it becomes in kilopascal. Okay, the pressure of the air increases from 0.8 bar to 1 bar during the ramming action of the air. Okay, so during ramming, what happens? Pressure increases from 0.85 bar to 1 bar. Okay, that means you will get pressure at point number 2. Okay, you will get the pressure at point number 2 equal to 1 bar. Okay, because 1 to 2 is a ramming. Okay, so after the ramming, what pressure increases? The pressure increases to 1 bar. So pressure P2 I'll just write down as 1 bar. So that is nothing but 100 kilopascal. So that is nothing but 100 kilopascal, right? 1 bar is 100 kilopascal, right? Next, the pressure of the air discharged from the main compressor. You can see the next statement. Pressure of the air discharged from the main compressor is 3 bar. Okay, pressure of the air discharged from the main compressor is 3 bar. So you can see here, main compressor is here. Okay, so what we want? We want the pressure of the air discharged from the main compressor. Okay, so at point number 3, the air will be discharged, because at point number 2, the air will be abstracted, and at point number 3, air will be discharged. So what pressure at point number 3 we have? 3 bar. Okay, so when you see this point number 3, okay, so whether it's point number 3 or whether it is 3 dash, both are on the same pressure line. So what pressure we have there? It is 3 bar. So I'll just write down here, pressure at point number 3 is equal to pressure at point number 3 dash, and is equal to 3 bar, and that is nothing but 3 bar. Okay, what is 3 bar? Okay, can you let me know what is 3 bar? Simple. Okay, 3 bar, it is nothing but, okay, 300 kilopascal. 3 bar is nothing but 300 kilopascal. Okay, so this is what is given in the problem, 300 kilopascal. Right. Next, the discharge pressure of the air from the auxiliary compressor is 4 bar. Okay, discharge pressure of the air from the auxiliary compressor. So auxiliary compressor, it is nothing but a secondary compressor. Okay, auxiliary compressor, it is nothing but what? Secondary compressor. So what is mentioned? The discharge pressure of the air from the auxiliary compressor is 4 bar. That means discharge pressure, that is nothing but what? Pressure at the exit of the compressor. So at the exit of the secondary compressor, that is at point number 5. Okay, so point number 5, or when you talk about 5 dash, they are on the same pressure line. You can see 5 or 5 dash, they are on the same pressure line. So what pressure we should have? Pressure we should have it equal to 4 bar. So I'll just write down here. Pressure at point number 5. Okay, pressure at point number 5. It is same as pressure at point number 5 dash, and that is equal to 4 bar. That is equal to 4 bar. And 4 bar is nothing but 400 kilopascal. 400 is 400 kilopascal. Okay, see here. Pressure at the discharge pressure, okay, from the auxiliary compressor. So auxiliary compressor is nothing but a secondary compressor. Okay, so it's discharge pressure. That means what? The pressure available at the exit. Okay, so exit is indicated by point number 5 or 5 dash, because when you see the point number 5 or 5 dash, okay, they are lying on a same pressure line. Okay, so pressure at point number 5 and pressure at point number 5 dash, they are same, that is 4 bar. Okay, it is mentioned in the problem. The discharge pressure of the air from the, you can see here, the discharge pressure of the air from the auxiliary compressor is 4 bar. Okay, now just see here, all of you. See, see what do you understand? What do you understand by this? Okay, point number 5. Okay, so that is point number 5 or 5 dash. Okay, it is nothing but what? 5 or 5 dash. It is the exit of the compressor. It is nothing but exit of the secondary compressor. Okay, now see what happens in a heat exchanger, secondary heat exchanger. What will happen? Only the air gets cooled. Okay, what happens in the secondary heat exchanger? Only whether it's a first heat exchanger or whether it's a secondary heat exchanger. What happens in both the heat exchanger? Only the temperature gets lowered. Okay, temperature decreases. Okay, but what happens with the pressure? Obviously pressure remains constant. So as you can see, whether it's a point number 5 or 5 dash or 6, they are on a same pressure line. Because see, when you start cooling it in a heat exchanger, what happens? Only its temperature decreases while pressure remains constant. So whether it is 5 or 5 dash or 6, okay, we will have a same value of pressure. Okay, so I'll just also write down this is equal to P6. Okay, because from the inlet to the exit of the heat exchanger, pressure remains constant. Okay, similarly here also I can write down P3 is equal to P3 dash, okay, is equal to P4. You can see point number 3 and 3 dash, okay, they are on the same line as point number 4. Okay, so here also I can mention that, okay, P3 is equal to P3 dash, that is equal to, okay, as you can see, okay, I'll just write down here also, is equal to P4, is equal to P4. Yeah, is that okay? Yes, is that okay or not? Let me know. Yes, let me know. I understand. Yes, I understand this one. Yes, 300 kilopascal.
Yes,
But P4. Is it okay? Is it okay with this one? Yeah, because see, this is the exit pressure of the compressor, that is P3 or P3 dash. Okay, so when you pass it to the heat exchanger, what will happen? Okay, the air gets cooled. Okay, but it occurs at what? Constant pressure. So whatever the pressure that is available at the inlet of the heat exchanger, same pressure you will have it at the exit of the heat exchanger. That is P3 or P3 dash. It is same as P4. Same thing is going to happen with this heat exchanger. Whatever the pressure that is available at the inlet of the heat exchanger, that is P5 or P5 dash, it is same as that of the pressure which is available at the exit of the heat exchanger. Yeah, is that okay? Yes, let me know. Is that okay? Yes, all of you, is it okay? Okay, yeah, you can respond. Is it okay? Okay.
Yes, sir.
Okay. Now see the next statement. Isentropic efficiency of each compressor is 80%, and while that of turbine is 85%. Okay. So that is the actual efficiency. As I told you, the vertical straight line like 1 to 2 or 2 dash to 3, 4 to 5 or 6 to 7, they indicates that they are having 100% efficiency. Okay, vertical line on TS diagram indicates it is having 100% efficiency. Okay, but what is mentioning? Okay, it is mentioned that the compressor is only 80% efficient while turbine is only 85% efficient. Okay, so that thing I need to write down now. So I'll just write down here. Okay, efficiency of first compressor, efficiency of compressor 1, it is 80%. Okay, similarly, efficiency, I'll just write down here, efficiency of compressor 1, okay, and efficiency of compressor 2, it is 80%. Okay, and efficiency of turbine, it is given as efficiency of the turbine, as you can see, okay, is 85%, right? Efficiency of the turbine is 85%. It is mentioned in the problem. Okay, so it is 85%. It is 85%. Right. Next, 50% of the enthalpy of the air discharged from the main compressor is removed in the first heat exchanger. Okay, what is mentioned? See, all of you, 50% of the enthalpy of the air discharged from the main compressor is removed in the first heat exchanger. That means what they're saying is, okay, we will get the value of the enthalpy, right? Can anybody let me know what you can understand by this statement? Yes. Yes. Enthalpy. See, 50% enthalpy of the air discharged from the main compressor is removed. Means at point number 4, you will get the enthalpy only as 50% of point number 3. Try to understand. You will get the enthalpy at the point number 4, okay, which is 50, because see what happens, the 50% get removed. Okay, the 50% of the enthalpy of the air discharged from the main compressor is removed in the first heat exchanger. So if 50% is removed, okay, how much is remaining? It's only 50% is remaining. Okay, so see, what is the enthalpy at point number 3? It is H3 or H3 dash. Okay, so what enthalpy at point number 4 you will get? 50% is removed. Okay, so at point number 4, you can see we will get the enthalpy equal to 50% at H3 dash. As you can see at point number 4, how much enthalpy we will get? At point number 4, we will get the enthalpy 50% at point number 3. Because why it is so? Okay, because 50% was already removed. Okay, so what is remaining? It's remaining 50%. Okay, so that is the reason. Next, and 30% of the enthalpy of the air discharged from the auxiliary compressor is removed in the secondary heat exchanger. Okay, just see the statement. And 30% of the enthalpy of the air discharged from the auxiliary compressor is removed in the secondary heat exchanger. See, what is the enthalpy which is available at the inlet of the secondary heat exchanger? It is H5 dash. Okay, it is H5 dash. See, H5 dash was available. H5 dash was available, and out of H5 dash, okay, 30% was removed. So how much remaining? How much remaining is 70%. Okay, so out of H5 dash, which was available at the inlet of the secondary heat exchanger, okay, 30% was removed. So how much is remaining? It's 70% is remaining. Okay, and that will comes at point number 6. Okay, that will comes at point number 6. Yeah, is that okay? Yes, let me know. Is that okay? Is it okay or not? Let me know. See, H5 dash was available. Out of H5 dash, okay, 30% was removed. So how much is remaining? That is 0.7 is remaining. Okay, so that will come at point number 6. Okay, that means that will be available at point number 6. Yeah, is that okay? Yes, is that okay?
Yes.
Okay, now see the next statement. assuming the ramming action to be isentropic. Okay, so we will have a ramming action that is isentropic. Okay, we will have ramming action isentropic. That means, okay, this point 2 dash will not be there. Okay, this point 2 dash there will not be there. Okay, so we will have an actual process. Okay, that means we will have only point number 2. We will have only point number 2. We don't have 2 dash point. Okay, we don't have a 2 dash point. Yeah, is that okay? Yes. The required cabin pressure of 0.9 bar. The required cabin pressure is 0.9 bar. Okay, so what do you understand by cabin pressure? So cabin pressure is nothing but, as you can see, okay, it is nothing but P7 or PA7 dash or P8. See, you will supply the air to the cabin. Okay, so when you will supply the air to the cabin, when it will comes out of the turbine. So whatever the air pressure that is available at the exit of the turbine, same will be supplied to the cabin. Okay, so here you can write down P7, or it is same as, so it is equal to, okay, that is nothing but a cabin pressure, and that is 0.9 bar. That is nothing but 0.9 bar. 0.9 bar. Okay, that is 0.9 bar, right? Next, the temperature of the air leaving the cabin should not be more than 20 degrees Celsius. Okay, so what is the maximum temperature that is leaving the cabin? So temperature that is leaving the cabin, that is 8. Okay, that is will be indicated by T8, and it should not be greater than 20 degrees Celsius. That is 293 Kelvin. Okay, 293 Kelvin, right? Okay, see, you can see this temperature of the air leaving the cabin. So at point number 8, the air is leaving the cabin. So at that point, what temperature we want? We want to be equal to 20 degrees Celsius. Find first power required to operate the system. Okay, that means they are asking to calculate the value of power. Okay, P they are asking. Okay, so P, this is a term in which they are interested. Okay, power they want. Okay, then COP. Okay, and COP of the system. Okay, and they are asking to calculate COP of this system. Okay, what is the COP of this system? So these are the things which they are asked. Yeah. Is that okay? Have you understood the problem? Okay. Solution now. Yes. Yes. Let me know. Can we start with the solution now? See, can we start?
Yes, sir.
Now see, in order to solve such problems, okay, the very basic step is you should be able to calculate pressure and temperature at every point, right? So if you are able to calculate pressure and temperature at every point, the problem will be get solved automatically. Okay, so let us start with point number 1. Okay, so for point number 1, okay, I'll just write down here. Okay, let us start with here. I'll just write down here. Okay, P1, V1. Okay, then P2, V2, P3, V3, P4, okay, V4, P5, okay, V5, all these things, okay, P5, V5, P6, V7, everything should be known. Okay, so we will calculate it. No need to write down those things again and again. Okay, so what we can do is, okay, let us start with point number 1. Okay, so at point number 1, whether pressure is given, pressure is given. Okay, temperature is given, P1 is given, T1 is given. So with point number 1, there is no any problem. At point number 1, pressure is given, temperature is given. Now go to point number 2. Pressure is given, P2 is given, but T2 is not given, T2. Okay, so as you can see in the diagram, okay, 1 to 2, okay, 1 to 2. See this point number 2 dash. Okay, this point number 2 dash will not be there. Okay, if you want, I'll just erase this point. This point number 2 will not be there, right? Point number 2 will not be there. Okay, so let us start. Okay, so see, when you talk about the process 1 to 2, process 1 to 2, okay, so process 1 to 2, it's an isentropic process. Okay, so I'll just write down here for isentropic process 1 to 2. Okay, for isentropic process, just a minute. Okay, let us start with the solution now. Okay, so I'll just write down here for isentropic process, for isentropic process, 122. 122 is an isentropic process. So when the process is isentropic, you can write down the relationship between temperature and pressure as T2 by T1 is given by P2 by P1 raised to power gamma minus 1 by gamma, right? So sort of equation you can write down only when it is isentropic. Okay. Further, you can extend is equal to V1 by V2 raised to power gamma minus 1. Okay. So I will not write down that because it is not required now. Okay. So from this, I will calculate T2 as T2 is given by T1 into P2 by P1 raised to power gamma minus 1 by gamma, right? So now let us calculate the value of T2. Okay. So T2 is given by T1, value of T1 it is given, as you can see, 293, right? Into P2, P2 is given 100 kilopascal, divided by P1, it is 85 kilopascal, raised to power gamma, it is given 1.4 minus 1 divided by 1.4. See, gamma it is 1.4, it is given in the problem now. If it is not given, okay, it is a ratio of Cp by Cv, and that we used to take it as 1 point. So from this, we will get the value of T2. Okay, so T2 we will get it equal to, okay, 306.8 Kelvin. This is the value of T2 what we got, 306.8 Kelvin. Okay, so this is all about which process? 122 process, because it's an isentropic. Okay, is that okay? Yeah, is it okay? Okay, now see, now let us move to 2 to 3. Okay, 2 to 3. If you want, okay, I can show that point here. Okay, see, then we will move to what? See, this point. See, if you want, I'll just. Okay. So now let us move to the point. Okay, 2 to 3. Okay, or 2 dash to 3. Let us take it about 2 dash to 3. Okay, so when you talk about this process 2 dash to 3, 2 dash to 3. So when you see this process 2 dash to 3, okay, it is what? It's an isentropic process. Okay, it's a isentropic process. Okay, is it okay? Yes. Yes. 2 dash to 3 is an isentropic process. Is it okay? Yes. Let me know. Is that okay? See, this point is, I'll just mark this as point number 2 here. This is point number 2. Okay. Let this be point number 1 only. Okay. So our process will be like this. Okay. It is 1 2 1 2 2. Okay. This is 1 2 2, then 2 2 3. Okay. We don't have 2 dash point. So I'll just clear this. I'll just clear this thing. Right. We don't have this point. Okay. We have the process starting from 1 2 2. That is see, because what is mentioned in the problem, the ramming is ideal. That means it's a straight line. You can see in the problem, it is mentioned that, okay, assuming the ramming action to be isentropic. Okay, so we will have isentropic ramming, that is 1 to 2. That means what? We will have it, okay, 1 to 2. Is that okay or not? Let me know. Yes. Yes, let me know. See, this is point number 2. 1 to 2, it's a straight line. We will not be having the inclined line. Okay, so 1 to 2, it's the ramming. Okay, now let us move to the next process. 2 to 3. 2 to 3 is an isentropic process, as you can see. Okay, so again, one more time, for isentropic process, so for isentropic process, okay, and that process is 2 to 3. For isentropic process 2 to 3, again I will apply the same. Okay, T3 by T2 is given by P3 by P2 raised to power gamma minus 1 by gamma, right? So I want the value of T3 now. I just want the value of T3. Okay, so I'll just write down as T3 is given by T2 into P3 by P2 raised to power gamma minus 1 by gamma, raised to power gamma minus 1 by gamma. So now let us put the value. Okay, so T3 is given by value of T2, we already know, 306.8. Okay, into P3, let us check value of P3, it is given 300 kilopascal. Okay, 300 kilopascal divided by P2, it's 100. raised to power gamma is 1.4 minus 1 divided by 1.4, right? So when we calculate the value of T3, okay, it will comes to be 420.3 Kelvin. Okay, simple calculation is there. I'm not showing those calculations. Okay, now see, so we got T3, right? Because 1 to 2 was isentropic compression, so we have applied this relationship between temperature and pressure. Similarly, 2 to 3 was again isentropic compression. Okay, so we applied the relationship between. Now let us, when you go to the point number 3 dash, try to understand 3 dash. You can't apply such relation for 2 to 3 dash because 2 to 3 dash is not isentropic, right? You can't able to apply. Okay, but see, this 2 to 3 dash indicates that, okay, the compressor is not 100% efficient. It indicates that 2 to 3 dash, it indicates that compressor is not 100% efficient. Then how much percent efficient? It is mentioned in the problem. It is 0.8. Okay, so by using that expression, that is efficiency of compressor, okay, we will calculate the temperature T3 dash. Okay, so by using the efficiency of this compressor, we will calculate the temperature, okay, T3 dash. Okay, so as I told you in the last lecture, okay, how to calculate this efficiency of the compressor, okay, because in the last session we have taken the numerical also. In that we have calculated how to write down. It is ratio of isentropic rise in the temperature, okay, to the actual rise in temperature, the actual rise in temperature. Okay, so what is actual isentropic rise? Isentropic rise is what? T3 minus T2, right? T3 minus T2, it's the isentropic rise, right? T3 minus T2 is the isentropic rise. And what is the actual temperature rise? It is T3 dash minus T2. Okay, only point number 3 will change to 3 dash, right? Because see what happens in a compressor, as I told you, compressor in actual condition requires more power than in ideal condition. Okay, so in actually it is consuming 2 to 3. Actually it requires 2 to 3, that is more it requires. But ideally it requires 2 to 3, that is lesser it requires. Okay, that's why this 2 to 3 it is longer as compared to 2 to 3 dash is longer as compared to 2 to 3. Okay, so now see, this is in terms of temperature. I told you. Okay, simple. I am telling you. See, this is in the form of formula. If you doesn't need to remember the formula, what I used to do is I used to see. I want an efficiency. Which should be less than 100%. Okay. So for getting the efficiency less than 100%, okay, the highest term should be in the denominator. Highest term should be in the denominator. Lowest term should be in the numerator. Okay. So out of 2 to 3 dash and 2 to 3, obviously 2 to 3 dash is a higher term. 2 to 3 dash is a highest term. So that 2 to 3 dash, I will keep it in the denominator. As you can see, 2 to 3 dash, I keep it in the denominator, right? And this 2 to 3, it is the lowest one. So that I will keep it in numerator. So you can see this 2 to 3, I will keep it in numerator. So by any manner you can remember this one, right? So now let us start it. So we have efficiency 0.8. Okay, it is mentioned in the problem. T3 we just calculated 420.3 minus T2. Okay, it is value is 306.8 divided by T3 dash that I supposed to calculate minus T2. Okay, T2 is again 306.8. So when I solve this, I will get the value of T3 dash. I'll just get the value of T3 dash, and it is coming to be 448.7 Kelvin. 448.7 Kelvin. See, simple calculation is there. That's why I'm not asking you to solve it. Okay, simple calculation. T3 dash we got, right? We got T3 dash. Right? Now see, we got T3 dash now. Every temperature we are calculating. T3 dash. Now I should get the temperature at point number 4. I should get now the temperature at point number 4. So how to get the temperature at point number 4? Okay, for that I can use this expression. What is that? H4 is 0.5 times of H3 dash. Okay, H4 is given as H4 is given as 0.5 times of H3 dash. See, this is given in the form of enthalpy. Okay, so what is H4? You can write down it is Cp into T4. Right? What is H4? Cp into T4. It is 0.5 times of Cp into T3 dash, because H3 dash is nothing but what? Cp3 T3 dash, right? So what we'll get the value for T4. T4 is given by 0.5 times of see, the Cp gets cancelled. What is remaining? It's 0.5 times of T3 dash that just we have calculated, that is 448.7. So by solving this, we'll get the value for T4. Okay, and T4 it is coming to be 360.85 Kelvin. 360.85 Kelvin. So this is the value for T4 what we got, right? T4 what we got, right? Now we got the value for T4. Now by using the expression for the enthalpy, you can see this enthalpy was given. We have used that. Now we are at a point number 4. Now we should get the temperature at point number 5. Again, 4 to 5 or 2 to 3 or 1 to 2. They are isentropic, right? So for 4 to 5, I will apply the relation. Okay, and what was that relation? For, I'll just write down here, for, okay, for isentropic process, okay, for isentropic process, that is 4 to 5. Okay, we'll just write down that. Okay, final temperature by initial temperature is given by, okay, final pressure by initial pressure raised to power gamma minus 1 by gamma. Okay, so if I equate these, okay, what value of T5 I should get? T5 I should get it equal to T4, okay, multiplied by P5 by P4 raised to power gamma minus 1 by gamma, right? Raised to power gamma minus 1 by gamma. So let us calculate now T5. T5 is given by T4. T4 just now we have calculated that term, right? T4 is 360.85. Okay. P5 by P4. Let us calculate P5. What is P5 value is given? P5 value. P5 it is given. P5 it is P5 dash. It is 4 bar. That is 400 kilopascal, right? That is 400 kilopascal. 400 kilopascal divided by P4. P4 it is again given in the problem. Okay, that is nothing but what? P4 is same as P3 or P3 dash, and that is 300 kilopascal, right? So divided by 300 kilopascal raised to power gamma 1.4 minus 1 upon 1.4. Okay, so from this we will get the value for T5, okay, as 391.5 Kelvin. See, this is the value for T5 we will get, right? So we got the value for T5 now. Okay, we got the value for T5 now. We got the value for T5, right? Also, I need to get T5 dash. So as to get T5 dash, okay, I can't apply the same expression because phi dash is the actual process. And see, phi dash, 4 to phi dash, you can see this 4 to phi dash, it occurs in a secondary compressor, okay, which is again 80% efficient. You can see secondary compressor, it is again 80% efficient. See, 4 to phi indicates it is 100% efficient. 4 to phi dash, it indicates, okay, it is less than 100% efficient, right? Then how much it is efficient? It is given, it is only 80% efficient. Okay, so here also I will apply the same logic. Okay, so efficiency of the second compressor, okay, as I told you, okay, just now I have written the formula, same formula. Okay, isentropic rise in the temperature, divided by actual rise in the temperature, okay, same formula. Okay, what I applied for the first compressor, as you can see here, isentropic rise in the temperature divided by actual rise in the temperature. Okay, so what is isentropic rise in the temperature? As you can see, T5 minus T4, okay, we'll just write down that is equal to T5 minus T4. Okay, that is isentropic. And what is the actual? T5 dash minus T4. Okay, T5 dash minus T4. Now let us put that value. Okay, this is 0.8% is given by T5. Just now we have calculated 391.5 minus T4. Okay, T4, what is the value of T4 we have taken? 360.85. 360.85 divide by T5 dash that I supposed to calculate minus T4. Okay, 360.85, right? So from this, I can calculate the value of T5 dash, okay? And it is coming somewhat 399.16 Kelvin, okay? So this is the value. See, simple calculation is there, okay? That's why I'm not asking to, or I'm not showing how to calculate it, right? This is how we got T5 dash, okay? T5 dash. So at point number 5, I got the temperature. Now I need to calculate temperature at point number 6. Okay, so for that I will use one more expression which is given, that is H6 is 0.7% of H5 dash. Okay, H6 is 0.7% of H5 dash, right? So that I will use now. What is H6? It is Cp into T6. Okay, it is 0.7% of, what is H5 dash? It is Cp into T5 dash. Right? So I'll get the value of T6 equal to 0.7 times of T5 dash. T5 dash is 399.16. Right? So from this, I will get the value of T6. Okay, and that is coming 361.3. See, I'm not more stressing on how this is, how to do this calculation. Simple calculation is there. No need to give more time for this calculation. Try to understand the things. So this is T6 we got, right? T6. We got the temperature at point number 6. Right? We got the temperature at point number 6 now. Right? Now again, 6 to 7. 6 to 7 is an isentropic process. 6 to 7 is an isentropic process. So for isentropic process, because see, temperature at point number 6 I have calculated. Now I should know the temperature at point number 7. Right? So 6 to 7 is what? Isentropic process. So again, I will write down here for isentropic process, for isentropic process, okay, 6 to 7, right? I will just write down, okay, what is that? T7 by T6 is given by P7 by P6 raised to power gamma minus 1 by gamma, right? So from this, I will get the value for T7 as T6. I'll just write down here. So T7 is given by T6 into P7 by P6 raised to power gamma minus 1 by gamma, right? So let us calculate now T7. So T7 is given by T6, that is 361.3. Okay, multiplied by P7 by P6. P7, let us calculate that, or let us see whether it is given or not. Yeah, P7 is given. Okay, that is 0.9 bar. So 0.9 bar, okay, I just forgot to convert that into, okay, so 0.9 bar, it is nothing but how much? How much? Multiplied by 100, right? So 90 kilopascal. It is 90 kilopascal. So P7 is 90 kilopascal. That I will write down now. 90 kilopascal divided by P6. What is the value of P6? Let us again check. P6 it is given 400 kilopascal. 400 kilopascal, right? This is 400 kilopascal. Raised to power gamma minus 1, that is 1.4 minus 1 upon 1.4, right? Upon 1.4. So by doing this, we'll get the value for T7, and it is coming as T7. We are getting 236 Kelvin. 236 Kelvin, right? Now see, so we got point number 7 now. Temperature at point number 7 we got, right? We got the temperature at point number 7 now. We got the temperature at point number 7 now. Now we should also calculate the temperature at point number 7 dash, right? See, 6 to 7, it's 100% efficiency. 6 to 7 dash, it's less than 100% efficiency, right? And this 6 to 7, as you can see, it occurs in a turbine. 6 to 7 or 7 dash. Okay, 6 to 7, it occurs in a turbine. Also 6 to 7 dash also occurs in a turbine. But 6 to 7, it is the ideal expansion. 6 to 7 dash is the actual expansion. Okay. So for turbine, they have given the efficiency. You can see the efficiency of turbine is given. Turbine is 85% efficient. That means, okay, on this dotted line, what efficiency we have? We have efficiency 85%, right? 85% efficiency. That means we will have a line 6 to 7 dash. Okay, 6 to 7 is 100% efficiency. 6 to 7 dash is a 85% efficiency. It is given in the problem, right? So I'll just write down that formula. Efficiency of the turbine. Okay, efficiency of the turbine. See, exactly reverse formula you need to write down. Okay, for the turbine when you compare it with the compressor. Okay, for compressor it is isentropic by actual. Okay, for compressor it is isentropic by actual. But for turbine, it is actual by isentropic. Okay, for turbine, it is to be written as actual, okay, by isentropic. By isentropic. Okay, and what happens in a turbine is in turbine temperature decreases. So actual drop in temperature, okay, divided by isentropic drop in temperature. See why the formula is like this? Because turbine in ideal condition always produces more power than in actual condition. Turbine in ideal condition. What is ideal condition? That is nothing but isentropic condition. So turbine isentropically produces more power as compared to the actual condition. That's why isentropic is more. That's why it is taken in the denominator, and actually it's less. Okay, that's why it is taken in numerator. Okay, so let us write down that actual drop in temperature. Let us write down that actual drop in temperature. So actual drop is what? T6 minus T7 dash. T6 minus T7 dash, right? So this is T6 minus T7 dash divided by, okay, what is the isentropic? What is the isentropic heat drop? It is T6 minus T7 dash. And isentropic, it is only. Okay, now let us put the values. We know the efficiency, it is 85% efficient. Turbine is 85% efficient. Okay, T6, value of T6, it is 361.3 minus T7 dash, we are supposed to calculate, divided by T6, 361.3 minus T7, 236. So from this, we will get the T7 dash. Okay, we'll get some value, 254.8 Kelvin. 254.8 Kelvin. So this is the value for T7 dash we got, right? Now every value we know. Okay. Now let us move to the, okay, let us move to the calculation of power. Okay, how much power is required for the compressor? All of you. Now we are in the last stage of the problem. Okay, we need to calculate now. Okay, what power is required for the compressor? Just try to understand this. Okay, power required for the compressor. See, all of you. Okay, I will just write down here. For power required for the compressor, how you calculate a power? I'll just write down power required for the compressor. Power required for the compressor. How you will calculate power required for the compressor? See, power is nothing but what? It is work consumed by the compressor, right? Because compressor will consume a work, okay, for which it requires a power. Okay, so work we used to calculate as WC. Okay, and when you divide by 60, okay, we'll get that power. Okay, because WC we get it in kilojoule per minute. Try to understand. WC, this quantity we used to calculate in kilojoule per minute. Okay, so when we divide it by 60, okay, try to understand. WC we used to calculate in kilojoule per minute. When we divide it by 60, okay, we will get the answer in kilojoule per second, right? We get the answer in kilojoule per second, right? So let us calculate first WC. Okay, let us calculate first WC. Okay, work required for the compressor. I'll just write down here. Work required for the compressor that we are supposed to calculate, right? How to calculate that? I'll just write down here. Work required for the compressor. Work required for the compressor. See, this derivation we already seen. work required for the compressor, it is indicated by WC. It is mass of the air, okay, into Cp of the air, okay, into change in temperature, into change in temperature. Mass of the air, Cp of the air into change in temperature. Okay, now as you can see on the in the compressor, okay, so for compressor, okay, see what is the initial temperature? Initial temperature is 2, and what is final temperature? It is 3 dash. Okay, see, ideally it should be 3, okay, but in actual it should be 3 dash. Okay, so initially is 2 and final is 3 dash. Okay, so I'll just take that temperature difference as T3 dash minus T2. You can see because actual efficiency is given, right? So we'll take final temperature minus initial temperature. Now when you see this formula, mass of the air we don't know, Cp we know, okay, T3 dash and T2 we know, but only mass is not known. Okay, we don't know the mass. Okay, so as I told you in the last lecture, okay, how to calculate mass. Okay, now I will not go into the detail of the formula. Okay, so see here, I'll just write down here mass of the air. Okay, that quantity I need to put, Cp I need to put, and this temperature difference I need to put. So how to calculate mass of the air? For calculating mass of the air, okay, we need to calculate the refrigerating effect. Okay, for calculating the mass of the air, we need to calculate refrigerating effect. Otherwise, okay, in the last that is simple air cooling cycle, okay, I already derived this formula. Okay, now I will just write down that formula. Okay, mass of the air. Okay, all of you, mass of the air is given by, okay, 210 into Q divided by Cp into T8 minus T7 dash. See, if you are not able to get it, I'll just erase it. Okay, let us calculate this. Okay, let us calculate first what is the refrigerating effect. Okay, refrigerating effect. Refrigerating effect. Where we will get refrigerating effect? We will get it in a cabin, right? We'll get a refrigerating effect in a cabin. Refrigerating effect we will indicate by Q. Okay, so how to calculate that refrigerating effect Q? Okay, so see all of you, refrigerating effect, that is heat absorb. Rather, I will call it as heat absorb. QA, heat absorb. Okay, it is a mass of the air, again Cp of the air into, okay, for cabin, as you can see in the diagram, for cabin initial temperature is 7 dash and final temperature is 8. Okay, so how much cabin gets cooled? Cabin gets cooled from 7 dash to 8. Okay, it gets cooled from 7 dash to 8. So refrigerating effect I will write down as, okay, T8 minus T7 dash. You can see from 7 dash to 8 it gets cooled. Okay, so 7 dash, all of you see this, cabin gets cooled. That means what? Air gets heated, right? So when air gets heated, the temperature will increase from T7 dash to T8, right? Is that okay, all of you? See, cabin gets cooled, as you can see in the problem. See, cabin gets cooled because why the cabin gets cooled? All of you, why the cabin gets cooled? The cabin gets cooled because the temperature increases from T7 dash to T8. You can see the temperature increases from T7 dash to T8. So when temperature of the air increases, obviously cabin gets cooled because air abstracts the heat from the cabin, right? So let us do that. Okay, let us finish it fastly. Okay, so when you calculate this one, right, mass of the air, okay, how to calculate mass of the air into Cp of the air into T8 minus T7 dash. Okay, but see, I want this refrigerating effect, that is Q. Okay, I want this Q. Okay, and the value of Q is given in tons. Okay, so how to convert that? That we already told you. Okay, so that Q, okay, I require 210 times of Q. Okay, because this Q is given in tons. All of you try to understand. Q is given in tons. Okay, so that ton I need to convert into kilojoule per minute. Okay, so I will multiply it by 210. See this Q, it is given in ton. Q is given in ton. So I will multiply it by 210. So it becomes in kilojoule per minute. Okay, so T8 minus T7 dash.
So let us put the value. Okay. So 210 into Q. Q it is given in the problem as 10 ton is given by mass of the air. I need to calculate Cp of the air. It is given as 1 in the problem. T8. Okay. Value it is already given the problem 293. Okay. T7 dash we already calculated 254.8. Okay. So from this we can calculate mass of the air as we get the mass of the air equal to 55 kg per minute. 55 kg per minute. We'll get this mass 55 kg per minute. Right? So by using this mass, okay, mass is 55 kg per minute. Cp is 1. T3 dash is 448.7 minus T2 is 306.8. Right? All of you can see. I told you the reverse column. Okay. So we'll get, okay, how much we're getting? Yes? Anyone let me know? How much we're getting? Yes, I'm asking too, how much we're getting? Yes, we're getting it equal to 780. 780, okay, kilojoule per minute. 780 kilojoule per minute we are getting, right? Divide by 60. Okay. Just a minute. Divide by 130. And this is 130 multiply. Okay. See, this is 7800 we get. 7800 kilojoule per minute. So when we divide it by 60, right? So 7800 divided by 60. Okay. So that we will get it in kilojoule per second. Okay. So that is nothing but kilowatt, and that is power, and that we are getting as 130. Okay. Kilowatt. 130 kilowatt. Is that okay, all of you? Yes. All of you, let me know. Yes. Is that okay? Is it okay or not? Now, how to calculate COP? It's the refrigerating effect upon work input. COP is given by refrigerating effect upon work input, right? So how you calculate refrigerating effect? Refrigerating effect, it is what? It is 210 into Q, right? Refrigerating effect, it is nothing but what? 210 into Q. 210 into Q. Divide by work input. Work input we already calculated just now. 7800. You can see this term. 7800 that we already calculated. 7800. So from this, see, COP is refrigerating effect, that is 210 times of Q. Okay, so we'll get an answer equal to 0.27, right? So what is the COP of this? This 0.27. Is that okay? Yes. Is it okay?
Yes,
Yeah,
sir.
is that okay with the problem? Let me know. Is that okay with the problem?
Yes, sir.
Okay.
Yes,
So
sir.
with this, we will conclude the today's session, and in the next session, we will see the reduced air cooling system.